Okay, I'm back. Uh, yeah, the first video didn't have any sound, and I'm sorry for that. So I just got better earphones. Like after that, uh, yeah, and let's get back into it. So we want to complete it today. Uh, so in the time that I was doing it, I also did some other stuff. Like I read a bit more while I was having dinner, etc. So where were we? So this is just like the usual, the conic section, inverse square law stuff going on. But now we are going to be doing something slightly different, which is the precession of Mercury. So Mercury has precession because of two reasons. One is that all the other bodies, their gravitational potentials are also interfering with the sun's gravitational potential, and that causes it to be sort of not be inverse square law anymore. It will be something more complicated. And the other reason, uh, which was very much unexplained till Einstein, uh, was because the gravitational force isn't actually inverse square at all. Like, I mean, yeah, it is to a very good approximation. It is inverse square, but then what Einstein said was that there's another component to it, which is to the power of 4. So it's r power negative 4, and that causes it to cause precession. So there are only two kinds of forces which can create closed orbits, which is harmonic oscillation and the inverse square law stuff. Okay, so let's just keep going. Planetary motion, few body problems. We were at. So we were just starting to read on the Ranglen's vector, and this isn't what we want. Yeah, so this is something different. Yeah, this is what we want. So the Ranglen's vector. So at the first glance, it seems that we can calculate the precision of Mercury to relativists. So I'm just going to write this down. Ranglen's vector. So this is actually a very simple concept. Just like the angular momentum and the energy are constant for our equations, right? For the whole thing, we want them to be constant. There's another quantity which is kind of constant when there's inverse square law, and that's called the Ranglen's vector. So we define it as this thing. So we define it as this quantity. So it's just vector p crossed with vector L. So L is the angular momentum. The angular momentum is pointing to the z-axis, right? Remember that. So the momentum, it will be basically be like what can you say? It will be rotated by 90-degree clockwise in a sense to give this P cross L thing. And so this thing minus mk. So remember, k is g and m, right? Yeah, so basically this thing is going to be capital G, capital M, small m squared. So just to be sure, G capital M small m, that has the units of force times meter square. This thing, momentum times angular momentum. So momentum, yeah, okay, angular momentum is like MER. Yes. Wait, what? No, not MVR. Wait, yeah, it is, right? Yeah. This thing is MV. Oh, there's also the mass over there. So, okay. So, G and M squared. So, it's like kg times R hat. R hat isn't really doing anything. Just a unit vector, isn't it? So, it's meter squared in terms of kg, and that times newtons, right? And this thing is momentum. So, we need another inverse second. That's what we're going to get from the angular momentum. This is MVR. So M is just mass, and then the speed is where we get the extra second inverse. And then apart from that, you also have 2 meter squares. So it all works out. Dimensionally, this is correct, right? and this thing is just something which is in the xy plane. This thing is 0 for the case of um, you know a circular orbit, because in the case of circular orbit, your angular momentum is tangential to the radial vector, right? There's no change in your radius. So in that case, your L cross P, it just turns out to be, sorry, your P cross L, it just turns out to be pointing to outwards, right, towards the radial vector, and its magnitude is basically that thing. It's mk r hat. So that minus mk r hat is 0. But then in the case of an elliptical orbit, it points towards, like this a vector, it points towards the, I think, perihelion. Wait, what was the thing? In the negative x direction. Yes, okay, so directly from the origin to the perihelion. So the perihelion is the point where the radius is the smallest. So that's also the point where we have theta naught, right? So the point when, yeah, I guess, right. So when we say like theta naught equal to pi, then we are setting it to be at that point. We are setting the whole thing to be at the perihelion. If theta naught equal to 0, we are setting it at, to be at the ephelion or something, right? So it's basically theta naught which changes, right? Yeah. This seems correct. So as theta naught increases, your point like goes in a clockwise direction from the perihelion to the ephelion, right? Yeah, and our angles are being positive when they are in anti-clockwise direction, just so you know, we're clear on the notation. Okay, so this points, this is 0 for circular orbits, and this is a constant, by the way, like this is a thing which is constant and points, it's a constant vector pointing to the perihelion, the negative x-axis basically. In case of closed elliptical orbits, and then by extension same thing for hyperbolic and paraboloid orbits as well, right? But then that's the thing, that we don't have inverse square law, and we don't have closed orbits either. In our case, we have an extra r power 4 r power negative 4 component, which slowly shifts the perihelion essentially. So the local orbiting is very much like inverse square, because the r power negative 4 thing is extremely small, so we don't see that, and so there's a kind of a sense of a perihelion, and that's where this vector will point to approximately. But then as time progresses, this changes slowly, and so we see that it's changing. Now this is good in theory, but then we don't really get this if we just do a normal numerical integration, even if we do just leapfrog, right? So if you remember, like I guess during my JEE years, I actually did a numerical simulation for something like this. It was a moon which was orbiting some planet, and it was going under drag, which caused its energy to go down. That wasn't quite as long term as we want it to be. In our case, we are using symplectic integrators because we want the energy to stay stable. it shouldn't deviate too much. uh, yeah. And if I had knew what this thing does back then, I would have used that, but here we are using this. Okay. So what does this do? It just points to the perihelion, and that perihelion shifts, and that thing, that rate of changing the perihelion is what we want. That's our rate of precession. So the rate of change of the angle that vector A makes with x-axis is the rate of precession. Now, to get the thing, to get a actual stable simulation, we can't just use the leapfrog directly. The problem with that is when the planet is really close to the singularity. Remember, over here the potential suddenly is 0, and then it's back to some negative values, right? No, not 0. The potential goes to infinity because 1 by r, so it just straight up goes to infinity or something. So over here there's a large singularity for the potential, and same thing for force as well. So like integrating over this thing, over this circle, is kind of problematic, because as you become really close to the sun, your forces are really large. Same thing with your speeds as well. The speeds are really large. So in each time step, you're going to have a lot of change in your state, and that's a problem. That will cause this to be going completely off if your planet is like really close to the sun. And that is the case with Mercury. So the other component, the other thing that you need is a slightly modified version of the leapfrog. So this is the leapfrog with time transformation. So this is what I read during dinner. Okay, so if you went ahead, calculated the Ranglan's vector with the leapfrog method, we would be disappointed with the results. We would see mostly noise for any meaningful practical step. The problem is that decreasing h is firstly not a good idea, because when you decrease h over here, when the velocities are actually very low, what this will do is it will cause rounding errors. Since the steps, like the update, is really small, and if you're doing, like, let's say fixed point arithmetic, your actual precisions, like you have 32 bits for example, your precision will be the problem at that point. Like your hardware is the problem. So decreasing h to an insanely low value is not going to solve anything. Sure, you might use floating values and then you do that, but then that will just make it even more time consuming. And if you just leave it at that, like let it run, maybe it's okay, but why do that when you have a better way, right? So just decreasing h isn't the smart solution. Smart solution is to have a variable h, that over here you have a large value of h so that you don't suffer from these rounding errors, but then over here you have a small value of h so that you can get a more precise simulation. So to do that, what we'll do is we'll have h as a function of r. So based on the distance from the sun, we will decide the time step. In particular, the sophisticated machinery that they have set is something like this. So these are your usual update equations. Your dr by dt is just the velocity vector, and your dv by dt is the acceleration vector. So we introduce a time transformation. So rather than just doing d by dt, now they'll do d by ds. So s is sort of like the arc length, and this is a fictitious time, sort of like on a log scale or something like that. I don't really know exactly what they're doing, but the way this works is that ds by dt is a function of r. So with a large change in a large change in t, you might have a really small change in s, for example, something like that. I don't really know what's going on. Yeah, okay, so ds by dt is omega r. That's what we want. Right, so we want like multiple s values at that particular point, isn't it? Yeah. So you want to like update s and not. So then as your r is, so whenever your r is small, for the same interval of time you want to have a larger interval of s, right? That's why you want your ds by dt to be a large value when r is small, and the function that we choose to do this is 1 by r. So we define so we scale the time step h based on the distance r with a scaling factor omega of r. Basically, rather than using t as the path variable, so this is like coming straight from multivariate calculus, but okay, as the path variable, like path parameter, we use s of t with the property that ds by dt, so just fraction which is basically our omega t, so omega r. This thing is large when r is small. This gives us, so now the update equations are these. Rather than figuring out how things change with t, we want things to be a function of s, because s is in the end a function of t, right? Yeah. So what we have is something like this. Okay, by the way, ds by dt equal to omega of r, that implies dt by ds is 1 by omega of r. That's just like normal. The same thing kind of goes for partial derivatives as well. Yeah. No, wait, okay, it doesn't, but I don't know what I'm talking about at this point. Anyway, what were we doing? Right, our update steps. So we'll have fraction d by ds. So now we need to solve for d of s and r of s. And then t of s, rather than okay, this gives us, this requires us to solve, or this means, so now our differential equations basically become d by ds of vector, let's say r, that's equal to the velocity vector, but then you have d by ds and not d by dt, right? So basically like you could do a kind of fraction stuff, yeah, and then multiply by ds by dt, so just using the chain rule. And then the ds by dt thing is just omega, so it's just omega of r times times the usual time derivative. So then d by dt of the velocity vector, sorry, the position vector, is just the velocity vector, so it's just vector v, and then omega of r. and then you have the same kind of stuff over here as well, except you have vector v over there. And now instead of velocity vector, you have the acceleration vector. Now this acceleration vector is a function of the position, right? And over here you have omega r again, right? And this is completely fine. Like at a particular time you can figure out what r is and do this thing, except if you remember in the leapfrog, what we actually do is that your what was I going to say, is that your r is actually updated, right? So you have something like your z is first updated by doing the exact what is it called, the exact transformation with just the t component, which is just the kinetic component, and then just the potential component, and both of these are linear in the end. So with just the kinetic component you update your position first, so that's the position wallet, and then at the middle of the step you update your velocity, and then again you update the position, and it somehow works out, right? Yeah, but in this case the problem is that once you update the position, your omega of r will change, and then we require the same time step for all of these updates, but then that won't happen. So we kind of want this omega r to be the same value, right? So in leapfrog, what the way we evolve, the way a single step works is through, so I know this notation is going to be like slightly complicated, but just stick with me. Vector z sub n plus 1 is equal to vector z sub n, and then okay, this is going to be slightly complicated. This is something which you people are probably not ready for, but here it goes. So first we exponentiate by dh, sorry, d, what is it, the first is the position which updates, right? The position updates based on velocity, which is going to update when you don't really care about the potential, it's just the t component over there, so it's just d sub t, right? And then you do it for h by 2, so t sub t h by 2, or h by 2 t sub t, anything works. And this is an operator. Yeah, I know this is like messed up stuff, but just deal with it. Like this is the way it is, and then you do a t sub v and then h, and once again an exponent. It's not like when like an e power something, this function is just basically doing a Taylor series in a sense. Yeah, I don't know what to say, because all of this was in like the last few assignments that I did, and it's hard to explain what's going on right now, but yeah. So in leapfrog, the way a single, so in position worlet leapfrog is through this thing, and thus we require h to be, or I'm just going to write it like this, to be constant, the time step, having varying time steps, having different time steps, okay, more like having time step r sub n plus half, that's omega evaluated at this thing, that times of h in the first sub step. Okay, actually this is supposed to be just omega r sub n. in other two will make it wrong. So we use the same step, call it W, which the same step scale W, which is computed at the very start. So our equations become these. So basically our updates are like this now. So we just have fraction. Basically we have the same stuff that we did over here. Just have this, except rather than having omega of r, you have a W, right? And then the W thing itself also changes. So you have how do you actually do this thing? I mean, this is basically like the change in omega r, right? Yeah. So it's basically just d by ds of omega r, which we know how to do actually. Oh, by the way, over here you should also have something about time. So you just have frac of d by ds of t. Yeah. So at this point, t is also a function of this s, which is our path parameter. So it's just dt by ds, which is, guess what, 1 by omega of r. I mean, obviously. Right. So this thing carries on as 1 by w, of course. So this thing is just 1 by w. And your w as well changes. So rather than thinking of w as, I don't know, wait a second. Yeah, I mean, I guess you could think of it later. The thing with velocity worldlet is that your velocity only gets updated once, and the changed position is used to compute that update. So if you use position worldlet thinking of w as some sort of a velocity, then this makes sense. Like you basically will be updating it only at the end and not beforehand while we are computing, and that's completely fine. So you can just put that directly into a leapfrog estimator, and it will be a leapfrog numerical thing, and it will be completely right. So rather than doing this d by ds stuff, I mean, I guess I'll just do it first. So remember, this r thing is changing as s changes, so we should basically be thinking of the r vector. So we think of the derivative of, so like omega is some kind of a field in a sense. Yeah, and it's the radial component which we really care about. Now we know the radial component is basically your b sub r, right, which is just a velocity vector's component along the radius, right? But even if this was some complicated function, if your omega of r, even though this time is simple, even if it was something like, I don't know, some complicated function which isn't just based on the distance but based on all the coordinates, what you would actually do is you would still be able to do this, is that you just take a gradient first, right? This tells you how does omega change with r, and then you multiply by the change in r itself, which is in this case dr by ds. So it's a c dot, which is our dot product, what am I writing? Yeah, and those are your equations. So this is what you do. Right, but then the same thing you can rewrite, because this whole thing you don't know what d by d r, so d by ds of vector r is, like that's kind of what we're trying to compute, right? I mean, using this thing, whatever, you can just put it over there. Once again, we're taking a d by ds and not a d by dt, but we want to take a d by dt because we know what that is. This is just a velocity vector, except the ds by dt thing, right? So we have to multiply by dt by ds, which is just 1 by omega. So we divide by omega of r. Yeah. Let me just preview it real fast. I don't like it here. Right. Or there as well, it is supposed to be by omega. It's supposed to be by omega. I don't know why it was like this. Over here as well, it should be like by w. I guess, yeah, that's about right. So it gives us these equations. Now that's the thing. Over here we have a w, but then this is a velocity vector. And our leapfrog estimators, they don't actually accept, sorry, a leapfrog code doesn't actually accept, you know, they don't actually, what do we say? They don't allow your velocity variables to be in the update equations for your velocity variables. So over here basically you can't have w, you have to have a function of r, which is omega of r in this case, because w is basically omega of r, except we are writing these equations so that they can just directly be put into the leapfrog estimator. The reason for still writing omega of r is so that it can be directly put, so that this system can be directly put into a leapfrog ODE solver, or more like leapfrog code. Code or something into a leapfrog solver function. In reality, that's not necessary. I mean, I don't think this is necessary. There might actually be some other reason, but this is not actually necessary. So this is like something doubtful. I'm just going to add a doubt to it. We could just compute the whole thing like this. Now, okay, I don't know what I'm doing. Before doing leapfrog, and update it separately. The good thing is that W can be computed directly because we are basically doing it as omega of r. But in any case, what they have actually done is that they have written this in a similar fashion to how you would write a Hamiltonian system, except this is nowhere close to a Hamiltonian system. Like if you look at their equations, what they're actually getting at is that r and t are to be treated as generalized coordinates, and b and w are to be treated as velocities. But then if you really think of b and w as velocities for the corresponding coordinates, so basically what we have is that w uh, is your ds by dt, right? Wait, what the hell? Hey, dt by ds is supposed to be w. Oh, what the fudge? I think they messed up a bit. I guess, yeah, even then it makes no sense, like, because their equations don't make any sense, like, in terms of Hamiltonian system. Even if this thing was d by dt, it wouldn't have made any sense. Like, the gradient being v vector by w and 1 by w, it's absolutely insane. It doesn't make any sense at all, right? How could it make any sense? Yeah. I mean, yeah, that's pretty much it. Okay, for this thing it has vector v and w as velocity vector, and doesn't even make physical sense since the equations don't correspond. Right. This is a more sane approach that I will take. Okay, so the question is why 1 by r, right? I mean, it seems a bit weird. Well, maybe the best way to think about it is so that your angular velocities will be the same, I guess. So you know that the velocity at the r min and r max differ by a factor of 1 minus the eccentricity upon 1 plus the eccentricity, right? So what we would want is that your r at that position and at this position to be, so your omega at the perihelion to be just that scaling factor, right? Yeah, yeah, I guess that makes sense. Since it's upon w, right? They want your time step to be multiplied by omega, right? Yeah. Wait, let me think about it. Yeah, so at a smaller r, you want your same time interval to get mapped to a larger interval in s, right? So you want your ds by dt to be omega of r, which would get bigger as r decreases, right? Basically, you want your increments to be lower when r is small. So that happens over here because you're doing, if you have omega of r equal to 1 by r and you're divided by 1 by w, then you're multiplying by r. And that works out, basically. Yeah. That's why they must have chosen it, because we want your, so yeah, the velocities are higher by a factor of 1 plus e upon 1 minus e. So we want our time steps to be lower by the same factor, so as to account for this. Yeah, I guess that is the correct way to think about it. But of course, you could have something else as well. Maybe you want the angular velocities to be the same. So the angular velocity is like that thing upon r. So that's actually something like 1 minus e upon 1 plus e squared, in which case you would have 1 by r square. Right. And now they have just derived the leapfrog algorithm for this thing. So just let's take a look at this. So first they're doing the half step. So over there they are just updating the positions, because that's position were let pretty big. What this does is, from the start they just add the velocities, and there you go, that's just the usual stuff. Then they do the velocity worlet step, so they do the velocity step. So you use this r of half to be doing the thing. So it's acceleration r of half h. That's right. I think that's more or less correct. Where's the w? Where the hell is the w? There should be an omega of r, right? Yeah, because when you do dv by ds, that's supposed to be a, yes, r of, oh, because it's divided by omega of r, it's just multiplying by r of half basically. So this is your 1 by omega in a sense. Okay, so you just did that. So now you're using r of half rather than the same w that you were using earlier. That's kind of different than what I expected, isn't it? Yeah. Hey, okay, this is very different actually, now that I think about it. This doesn't correspond to a physical system, so why would they do this? doesn't make any sense. I mean, there is no actual t which corresponds to something as weird as this thing. So how come neither does this as velocity make any kind of sense? How is this happening? What is going on? Yeah, this makes no sense at all at this point. If you're thinking of the Hamiltonian system where s is representing a time derivative, I mean s is just representing a time in a sense, and these are our velocities, your v vector and w, right? I'm guessing that's what we're trying to do. Then this thing is absolutely insane. What even is this? Like, no, it doesn't make any sense. This is messed up. Like, why is this equation going to give you the correct value? The actual fuck of half, they said. They're using W naught to do this thing. And then they're using the same R of half to just update W. So I'm assuming let's assume the W thing is entirely correct somehow. Even then, the way they're updating these, this should not work. This should like fail, but this isn't quite correct because we're getting something very different. Okay, this is just raising more doubts than it's answering. Huh. Okay, in their update equations, they don't actually have the same scaling factor. Yeah, I mean, this is what I find the most boggling, I guess. How does this even make sense? For the sub updates, I actually don't understand what's going on. Come on, let's try to think about it. So t half is that, and then t1 is just this thing, but then t half isn't really used for anything else, so that's fine, I guess. Yeah, so over here it's like h by 2w0, and then here it's 2w1, so these are different time steps that they did. Interesting. Why that? Because the r value is changing. The r value is changing. This is not making any sense at this point. I really don't know what's going on. Can we do the same kind of algebra that we were doing for that thing, that you could like t sub t basically. Because over here you don't even have a proper t as such, so what's going on? What the hell is going on? How does this make any sense? Anyways, I'm just going to accept it for what it is, because I don't know. But okay, move on. The update are, so let's just write down what they're doing. So they have r half, it should all just be vectors. So copy this thing because it's cumbersome to write. So vector r sub 0 plus vector v sub 0 and then h by 2w 0 right. So h by 2, and then I'm going to write it like as 1 by w0, 1 by w0, right. Then you just have t half is just t0 plus once again h by 2 and then the scaling factor, which is 1 by w0. Interesting. You really got to think about it. What's going on? It's a different one, isn't it? Yeah. Is 1 times step upon omega, sorry, on w, and w is just omega of r, which is just ds by dt. So it's, what is this? H is just a small step in ds. By having this thing, what are we trying to accomplish? dt by ds isn't what we're trying to do. Okay. Could it possibly be? So could it possibly be that h corresponds to a ds step? Yes. Then h by this factor would correspond to a dt step. Yes. and with v1 you are having r half, which is not the same dt, is it? Yeah, you would require the step size to be small for the same thing, but then you're not actually doing that, are you? So didn't they say that your dw/ds stuff, it shouldn't have anything related to velocity, and then yet they have this v vector over here? This doesn't make any sense, does it? We wanted separability, didn't we? Yeah, and yet we see them not following that. I'm just lost what's going on. Like, this part I just do not get. Anyway, I'm just gonna write down these equations. Put the same thing, I guess. You could just have a reactive steps, right? What's the big deal? Why do all of this complicated stuff? Doesn't make any sense. Why would you do this? Just compute it directly. Yeah. Why would we be doing this? How is this different from just changing the size of the step? Wouldn't that pretty much be the same thing? But no, it isn't, because look at these equations. It's just complete bullshit going on with them. What is this? Why are we doing all of this? I never felt so lost in all of this. I mean, what's going on? I get it, the gradient and all that, but still. And then the final equation. No, not the final equation, there's more. this particular thing. This makes no sense. Vector v isn't actually a function of r. Do you not want this to be completely a function of r? Yeah, what's going on? V changes, everything changes, doesn't it? It does. So how could you actually solve this? It doesn't make any sense. Moreover, you're doing this weird average over there. What does that even mean? Like you want a half step and so you just take an average. Well, that's stupid. Doesn't make any sense. It's as if you've done some RK2 stuff. Okay, let's just keep moving. Like, okay, you have some weird way to solve it. Then simulation of differential precision. Finally, we have all the necessary parts to calculate the relativistic correction to the precision of Mercury. Putting it all together, we give the complete simulation in program 4.3, and the simulation with animation on and enter lambda large enough, say 0.01, to see the exaggerated effect of precision should be similar to figure 0.6. You should also see that the motion of the Young length vector is not uniform. It rocks back and forth while the mean motion forward in the same direction as the circulation of Mercury. Okay, so this is like for the full thing, for like I guess a century, and this is also for a century. No, okay, this is for the last 2 years, so it's like oscillating more or less. Likelihood we can exclude numerical error as the cause. And so certain oscillations are real. What is the physical reason for them? We note that there are about 4 oscillations per year, but the period is about 1/4 year. This is just the orbital period of Mercury. Therefore, the oscillations might be connected to the orbital period. Observe the phenomena visually. Let us assume that Mercury starts at the period going counterclockwise. The Young length vector. The y component has 2 terms formed equation. this is just like they're giving us assignments on what to do, what not to do, which I guess I can just do at that point and see the thing for myself. Okay. So Mercury interacts with other planets through pairwise forces that are not central related to the Sun. A general description would need take into account all the planets simultaneously. A many body problem. But if the effects are small and if we are interested in only the average values, like precision over a period of time, we can approximate each pairwise force as a central force and treat it individually. The idea is that Mercury moves around the original Sun basically rapidly, and the average force points in the radial direction. In such case, we speak of the central field or mean field approximations, which are very useful and important in many areas of physics. If we construct a force between Mercury and planet in a central field approximation, we can calculate the precision of Mercury to the force with the same methodology as the relativistic effect discussed. Okay, why are we doing this? Oh, okay, I think I get it. Because the frequency of Mercury orbiting the Sun is not like is not in sync with the frequency of some other planet orbiting the Sun. So over centuries, you would have you would basically be having like the effects piling up at all the different R values that you would want, and so it behaves as if like a ring was putting that force. So it makes perfect sense to be doing this. It's as if nature itself is doing a sort of numerical integration or something like that of its own. It's integrating over the different R values that the other planet should be at. Yeah. Sorry, over the different R values that the elements of the what do we call it? The this thing. What is it called? The infinitesimal element of a ring would be, or a disk would be at. And so we can do this actually. This isn't so bad, I guess. So distribute the planet over its orbit. It's weird, but that's the way it is. They are not even doing that, they're just distributing over a coplanar ring of radius a. right? I guess that is the thing. We can do something even simpler. And just consider a circular orbit. Making the ring uniform. Then the gravitational force, the relativistic, by the way, relativistic gravitational force. So remember, the inverse square gravitational force will just like become zero, because this is something we have done now. Gravitational force will be like a coplanar ring of radius a. Mercury is, I think, the closest, so how would you have something like this? Okay. What's going on over here? The roads are by A. What is theta over there? I'm just integrating over theta. Isn't the position supposed to be different or something? Yeah, I mean there should be like two angles, isn't it? Force is central. That is correct. But then okay, what's going on? This is starting to not make sense. Why is this? Oh, this is a potential. I see. Okay, cool. Fine. So that's the potential, but we just want the force really. Okay. I don't get it. Okay, so you have this thing. The potential is different. Okay. But then it's just a disk, so this shouldn't really happen, should it? It's just a ring, isn't it? Yeah. Oh, it's just R by A. What is going on? What is going on? Okay, R is, I'm assuming, is the Mercury's distance from Sun. So then you just have 1 plus rho square minus 2 rho cosine theta. Okay, that's fair, I guess. Just doing a dot product of sort. No, okay, it's more like difference of two vectors squared, isn't it? Yeah. Yeah, that makes sense. Sure. Like, compared to the planet, this is at a row, okay, and this thing that we're taking about set cosine theta, sure. So the element is a cosine theta. Let me just do this thing. Fine. Now that's your 1 by r, and then you just integrate. There you go. That's the potential. This is the function of theta. Fair enough. So just got to take a derivative, isn't it? That's a b of r, by the way, not even a function of theta. Okay, cool. Theta is like changing. Okay, so I take a derivative with respect to r. What do you get? Hey, this is stupid. Okay, so now you're doing a Taylor series, and then you're taking a derivative, and then you're getting the force. What I don't get it is, why didn't you just take a derivative beforehand, before doing this Taylor series bullshit? Yeah, I mean, what's going on? Like, would you would just get something like 1 upon, um, you know, this is like 3 by 2, so it's just 2 by 3, and then that to the power of 3 by 2. Wait, what? Integration. So it's like, okay, it's square root of all this stuff. Wait, no, I'm doing something weird with it. So the negative half comes on the top. This thing is just gonna become some 3 by 2 stuff, and then the derivative of the inside, so that's just like 2 rho minus 2 cosine theta, and that times the derivative of rho, which is just 1 by r or something. Fair. Now it's 1 by a. Okay. Now that's like kind of constant, isn't it? What you're left with is just a 3 by 2 thing, and then on top of that you have the negative cosine theta, right? Now the negative cosine theta thing can be killed, if I'm not wrong. Can it be? No, it can't be. Can't be. Ah, that isn't that great. The potential is this thing. Wasn't it something like that the force exerted by a sphere for an inside object is 0? But then over here you're not actually doing that. Sorry. Isn't this force supposed to be 0? Having the potentials. Should it be 0? That's what they do with electrostatics, isn't it? That the electric field inside should be 0 or something like that. Yeah. So why isn't the same thing happening over here? Let me just check though. Am I wrong somehow? Force due to uniformity. Gravity. Gravitational force due to uniform ring. Because we have the same thing with electrostatics, and it's the same power law, so why would this be wrong? It's okay, it's 0 at the center. Okay, no, this is not what I want. It's doing some weird shit. Uniform coplanar ring. So they're saying it's an elliptical integral, but then instead of a shell, it's 0, right? Okay, so by that logic, even for a uniform coplanar ring, okay, the electrostatic force should also be 0, right? No, it shouldn't be 0 in that case. Yeah, I guess so. It's the same, except it isn't really 0. It's this massive problematic integral. So it's not the relativistic. So it's the non-relativistic gravitational force, gravitational potential actually. Will be this thing. I'm just gonna write this out, this exact equation. Because turns out this is probably the only way to do it. So this is g mass of the planet times the mass of Mercury upon 2 pi a. Why 2 pi a? So by a I get, but why 2 pi? Because 2 pi r, right? Yeah. So it's basically 1 by 2 pi a times the length. So just integral from 0 to 2 pi. You know what, I'm just going to remove most of it. So m by 2 pi is basically the density, and then yeah, you're basically implicitly multiplied by the density at the end, and I just want the arc length. So then d theta is the arc length, right? So like r d theta, but sure. Potential for such a planet with orbit radius r or orbit radius a, and the Mercury is at position, is at distance r from Sun, will be, and it's given. So you just want this whole thing, so it's just write that down, d theta upon the square root of 1 plus rho squared minus 2 rho cosine theta. Yeah, cool. That's about it. Since rho is less than 1 for Mercury and any other planet, we can Taylor expand this as, and okay, as basically, so we'll just like have till some particular order. So I'm guessing they are going to do just the first 3 terms. The integrand actually. Yeah, I guess so. Because right, so they just have was done the other thing, right? Huh. You just have the power of negative 1 by 2 and then you Taylor expand that, right? So it's just this thing. 1 by 4 and 9 by 64 and all that. What's going on? Is that how we do it? Or is something else going on with it? Think about it. Okay, so that we have cosine theta in any case will just be 0. Sure. And what else one thing? Come on, think about it. How did they get to this? The power series. Oh, so this whole thing can be expanded. It's not Taylor expansion. It's something weird that they did. Somehow expand, write this as a power series. Okay, cool. So the one basically dies. Ah, well, I see what's happening. What happened to the R though? Okay, they actually took it out. Fine. So it's all the way till the third one. 9 by 4, rho power 4, and then just have 25 by 256, then rho power 6, I guess. I see. And then plus order rho power 8, right? Then we get the force, we take the gradient to get the force. So all we really have to change is to change the acceleration, but it's fine. So it's just fraction and then the acceleration. So then it's rho power 8 over there. One of them got killed, one of them got taken up. So it's rho power 6 essentially. So up to a rho power 6 this works. This force is repulsive, radially outward. Okay. Repulsive away from the sun, essentially. Lingdom behaves like Hooke's law. Note the sign. It's away from the sun. Mm-hmm. The interplay between the two parameters using the force and the central field approximation. With the parameters, we obtain the results of table 4.2. I see. So, due to the other planets. I see. In between, the order reflects the balance between the radius and the mass. Note that the results for Earth are obtained with combined mass of Earth and the moon Neptune. Oh, okay. Neptune, the outermost planet, gives the smallest contribution because of its large radius and moderate mass. Hey, wait a second. The radius of the orbit, of course. Yeah. Scaling laws in the central field approximation. Wait, what does that mean? Oh, okay, so they're just trying to find a trend. So for small perturbations, we expect precision to scale linearly with mp by a cube. So a linear scaling law. Varies over 3 orders of magnitude, similar to the precision results in table 4.2. If you study precision versus the scale variable. Okay, so now they have the data. So now it's mp by a cube and it's kind of linear. Okay, fine. So far it's just this Mercury stuff going on. And then they move on to something entirely different, which is star wobbles in exoplanets. Extrasolar planets or exoplanets, including Earth-like planets and planets in the habitable zone, supporting an atmosphere and liquid water. Huh. So what is the star wobble though? Large mass ratio. Oh, okay, because yeah, I see. Because the planet is also causing it to revolve, right? So the center of mass, it's not exactly at the star. I see. Measuring the wobble of a star. Light blocked off an exoplanet pass in front of a star, and light bending and brightening due to gravitational fields, among others. Oh my god. this is some great stuff going on. They're using the Doppler shift, moving about the center of mass will be Doppler shifted. Velocity of the star along the line of sight. Oh, so at the point where, so it's like at the point where the radial vector from the center of mass is perpendicular to the line of sight, which is when the star will be moving at like either parallel or anti-parallel to your line of sight, you're going to get the greatest Doppler shift, right? So now they're trying to measure the Doppler profile. This is some great stuff going on. I mean, okay, so I read like a lot of medical imaging, as you all know, and there they're using Doppler shift for similar stuff like detecting when things are moving, and here they're using the same thing except with light. It's great, really. It's of course different. Like with light, it's a different reason that you get Doppler shift, and the equations aren't the same that you have for sound, because you have relativity, right? That is the reason you have Doppler shift. But yeah, I mean, all this is like very, I guess, similar to each other, isn't it? Huh. Yeah, I guess I get it. So at the point when it's like this, it's going to do the thing. Okay, so this is like a lot of math that I'll have to read. Probably less complicated math, but math indeed. So yeah, I guess I'll do it once I'm done with the first two mini projects. The first mini project is about seeing how Mercury orbits. Second is about this precision, and then the third will probably be about this thing, exoplanets. Alright then, so see you guys in the next video.